A ver si me contestas.
¿Cuándo quieren empezar? ¿En unos 5 minutos o ya?
¿5 minutos?
Muy bien.
5 minutos.
Ajá.
¿Se puede hacer la introducción? ¿O alguien me lo dañó?
¿Sí se escuchó?
Creo que están haciendo otra cosa. Me preguntó que si se escuchaba, pero...
¿Y ya no respondieron?
Ajá.
¿Sí se escucha?
Sí, sí se escucha bien.
Hola.
Sí.
¿Sí se escucha?
Dice que sí.
Ok.
Solo en cuanto nos digan, decirle a Alejandro cómo abrir el micrófono y
Ok.
comenzar la transmisión.
Sí, no puse el programa y puse un ratito.
Bueno, podemos Classical Quantum Stochastic Systems, algo así. Hoy tenemos a Dávalos como ponente. Él hizo su doctorado en la UNAM con Pauli-diagonal, algunos de ustedes no lo conocen, en el área de computación cuántica, y hizo un postdoc corto en la UNAM también, y de 2021 estaba el postdoc en Eslovaquia con Mario Sima, pues también trabajando en computación cuántica. Y ahorita trabaja en una empresa de inteligencia artificial y pues también en la academia. Pues, nos va a platicar de su proyecto, de su trabajo sobre canales cuánticos, y pues es un placer tenerlo aquí.
Gracias, Tomás. Okay. Entonces, ¿está bien en español?
Ahora sí podemos preguntar, ¿quieren en español o quieren en inglés?
El que se siente más cómodo está bien.
Pues, si todos hablan español, pues español, ¿no? Sí. Ok, pues, primero que nada, quiero agradecer a Tomás y a su grupo por darme este espacio para platicarles, pues, lo que ha sido mi trabajo en los últimos años. Básicamente les platicaré parte de lo que se hizo en mi doctorado, que es algo que llamo los resultados viejos sobre divisibilidad de canales cuánticos, para poderles así platicar un poco mejor los resultados nuevos, que de hecho se publicaron apenas este año. Después también platicaré de otros dos proyectos que también son recientes. Este de aquí exploramos un tipo particular de ruido que pensamos que puede suceder en los experimentos. Y la teoría se construye pues, utilizando canales cuánticos. Y después, otro proyecto en el que estudiamos una familia en particular de canales cuánticos. Esto es porque, como lo verán más adelante, los canales cuánticos pues en realidad son un zoológico, entonces hay que buscar familias razonables para poderlas estudiar, ¿no? Entonces, pues la introducción se enfoca en platicarles o recordarles que es un canal cuántico, de una forma quizás un poco más matemática. Son canales, son mapas lineales que cumplen con estas propiedades, que es que sean positivos y preserven la traza, pero en particular también pedimos que sean completamente positivos. Si ven ustedes, estos dos requerimientos nos permiten mapear matrices de densidad a matrices de densidad. Sin embargo, dado que la mecánica cuántica admite correlaciones no locales, pues resulta que se necesita un requerimiento más, que es el que llamamos completa positividad, que nos garantiza que cualquier dilatación de nuestro sistema y nuestro canal, digamos una dilatación de cierta forma trivial, en el sentido de que lo que se aplicará en la parte extendida es la identidad, lo que requerimos es que el estado de la dilatación también se mapee a un estado cuando aplicamos E, que en este caso pues sería localmente. ¿Sí? Entonces, pues, estos son el objeto central que se estará utilizando a lo largo de la presentación. Y entre las propiedades y herramientas que uno utiliza cuando trabaja con canales cuánticos, pues es, o sea, uno observa que el conjunto de canales cuánticos, que también les llamaremos simplemente mapas CPTP o el conjunto CPTP, es convexo y aparte tiene una estructura de semigrupo que es interesante porque captura el concepto de irreversibilidad. O sea, los únicos canales que son reversibles son los unitarios. Son contractivos, entonces capturan la pérdida de información, entonces nos modelan ruido. O algo así como la contraparte cuántica de lo que se puede pensar como una evolución estocástica. Los mapas CPTPs, aparte, se pueden dilatar con algo que se llama dilatación de String. Y básicamente lo que nos dice es que si ustedes tienen un mapa CPTP, entonces a este lo pueden reescribir como el esquema usual que uno usa cuando estudia sistemas cuánticos abiertos, ¿sí? También tiene su representación de Kraus, que es aquí, y una herramienta que uno usa es el isomorfismo de Choi-Jemelkowski para caracterizar que el mapa sea completamente positivo, es decir, si la matriz es positiva semidefinida, se dice que el mapa es completamente positivo, ¿vale? En tanto a otras definiciones que nos serán útiles, es la de mapa dinámico cuántico, que se define así, en donde usualmente la T pues, es el tiempo. En particular, si en todo dominio o en algún intervalo de interés el proceso es diferenciable e invertible, este admite una ecuación maestra en donde el generador pues, se define así. Algunos tipos de evoluciones que les pueden sonar familiares, pues es, por ejemplo, de la ecuación maestra markoviana dependiente del tiempo, que es esto que está aquí, en donde el generador pues, depende del tiempo, la solución formal es esto que está aquí, o las ecuaciones markovianas o evoluciones markovianas independientes del tiempo, que son las que están aquí, que tienen esta solución formal, que lo interesante que tienen estos sistemas es que una evolución, o si quieren ver como una trayectoria en el espacio convexo de canales cuánticos, que comienza en la entidad, pues forma un semigrupo de un parámetro, en el que el generador es un canal que es simplemente E a la N, ¿vale? Entonces, esos canales, estas evoluciones, o en particular canales con esta forma, serán de particular utilidad a lo largo del trabajo. Ahora me iré a los resultados viejos en tanto a divisibilidad. Primero que nada, la definición de que un canal sea divisible es la siguiente. Se dice que E es divisible si existe una descomposición de esta forma en la que ya sea tanto E1 como E2 son unitarios, lo que significaría que E es un canal unitario, o ambos son no unitarios. En ese caso es no unitario. La definición es así porque si permitimos que E1 y E2 puedan ser lo que sean, pues todos los canales son trivialmente divisibles, porque uno siempre va a poder descomponer un canal en otro canal y una unitaria, porque las unitarias se pueden ver simplemente como un cambio de base. ¿Vale? Entonces, en este trabajo lo que quisimos estudiar es, pues, cómo se conectan los tipos de divisibilidad con formas particulares de evolución, en el sentido de que si ustedes me dan un canal que tiene ciertas propiedades de divisibilidad, entonces, ¿con qué tipo de proceso lo puedo implementar? ¿Sí? Y la motivación viene, por ejemplo, de que si ustedes tienen un canal unitario, que está aquí, uno siempre puede definir un hamiltoniano por el teorema de Stone, y entonces, en este caso, el canal unitario es implementado por esta dinámica al tiempo t igual a 1. Entonces nos podemos preguntar si en general para cualquier otro canal E, si uno puede escribir E, por ejemplo, como E a la L, que les recuerdo que eso significaría que se puede implementar con una evolución markoviana independiente del tiempo, por ejemplo. Pero bueno, resulta que la respuesta es no se puede hacer eso, y en realidad es bastante simple, porque resulta que si un canal tiene esta forma, entonces su determinante es no negativo, y pues resulta que existen canales que tienen determinante negativo. Y uno se puede preguntar por otros tipos de divisibilidad más restringidos. En esta parte, en realidad, no quiero enfocarme en todo porque no me va a alcanzar el tiempo, pero en resumen lo que hicimos en este trabajo fue, en parte, caracterizar cómo están incluidas las clases de divisibilidad en el espacio convexo de canales cuánticos. Want me to switch to English?
That will be great. Thank you.
Okay. Yeah. So for instance, basically, we prove things such as that the intersection of this set with the set of indivisible quantum channels is non-empty, among other things, such as the characterization of the set CL that corresponds to the set that we call L divisible channels, that are exactly channels with this form. I will also a relation with entanglement breaking channels with channels that are not inside CP. But I want you to focus in this type of channels from now on, right? Some figures that are basically the idea depicted here, but for Pauli channels and for a family of let's say of deformed non-unital Pauli channels. So the idea here is that you can see some properties, for instance, of the set CL that we already know from the theory, but you can see it here graphically, is that the set CL is non-convex. Also, the set that contains only channels that can be implemented with time-dependent Markovian equations. That is, I think, the purple one and so on. Yeah, but well, I want to go. I want to explain more the new result now. Any questions so far? Okay, so in this second work, we wanted to answer the question if there are channels that are divisible, for instance, in two divisible channels, but not in three, or more generally, channels that are divisible in n divisible channels, but not in n plus one. So, but it turns that the answer is no, at least for the qubit case and for general finite dimensional full Krauss channels. That anyway, they happen to be the generic channels in the sense that they enjoy of measure different from zero in the set of quantum channels. And to prove that the last statement is true, we found a very interesting result, in my opinion, and is a new decomposition of any finite dimensional quantum channel, and it will be following. Given any channel of dimension d, in the sense that the underlying Hilbert space has dimension d, we can decompose E in a channel that lies in the boundary of the convex set, and in a channel that has this specific form. So this decomposition is similar to the polar decomposition, at least in a fashion, but this EL contains, by definition, a Hamiltonian part and a dissipative part, right? And well, some remarks is that if E is non-singular, that is that the inverse exists. The composition with the opposite order also holds, and it turns out also that always we can choose L to be pure dissipative. And the sketch of the proof is quite simple. The idea was that for any channel here, you can find some L, some Lindblad generator of the Markovian master equation, and then you, let's say, reverse the dynamics this way. I mean, you compose this parametric family with, for instance, this channel here, that is the blue dot, and then eventually the idea is that you get out of this CPTP set, and the idea is was to prove that for every channel you can always find this L, and that for every channel you can always find this intersection point. So the idea is that you look for this point, and then you define the boundary part, and then just you just solve the remaining equation for the original channel, that in this case is the blue dot, right? So there are, of course, a lot of mathematical details to be aware of, but the idea of the proof is this one. Question, Thomas?
Yeah, I haven't understood anything.
Maybe if I
So, I mean, the dot, the red,
Yes.
the red or the blue dot, they are channels.
Yes.
And then if you go from one channel, e to the minus t L2, I mean, the blue dot out of the CPTT,
Yeah.
this is another channel.
No. Look, the composition of e to the minus t L2 with the blue dot is outside for some t.
But the composition.
Yes.
Ah,
Yes, it's small.
no, but it's still not what you want, right? Because the blue dot in the center is E. Now
Yes.
you say I have E, I take the composition with some E to the L, and then I can get outside.
Yes. For
Yes.
yeah. So
And then,
basically, there exists something such that this ft is not CPTP.
but still, no, I don't see. So now you have E, so you can find the intermediate T such that this F is on the boundary.
Exactly.
But that's not what you want to do, right?
Yeah, no, the idea is that this curve is just this family of
So you
channels.
take then the inverse
Yes,
of, so take, say, positive. Now you have negative times, and then you take positive times to get.
exactly. So
Can you write this down?
what?
So now you find the T such that
Yeah,
E boundary is equal to E to the minus TL E.
yes. So this is
E boundary.
for the exact time.
And now you flip to the other side.
Yeah, and just define the new L as just T.
Well, it's the same L, you just switch the sign of T. I mean, so this E to the minus, okay, so this E to the minus T L, this is not a contracting channel, it's what's the contrary.
Yeah, but the idea is that at the end you will preserve it to positive line.
Yes.
Yeah. Okay, so
But
yeah.
so what is the difference between red and blue?
They are different channels. So for instance, for this channel, I take L1. For this channel, I take to also L1. So, but since the starting point is different, then the cube is different, and then I put here intentionally two lines to show that the composition is not unique.
Oh.
Yeah. Yeah. So, and
Also, for each channel, you need a specific T in order to achieve this.
I mean, once you have a channel E, you have to find an L that brings you out of the set, and then you find T. That means that you prove that for that particular T, you're in the boundary, and then just the rest. Yeah. But the idea here is that we prove that such L and such T always exist. Yeah. Okay, so the applications of this theorem is exactly the non-existence of this of strictly indivisible channels, at least for the full Gauss run case, and that fact follows directly from the infinitesimal divisibility of L, because E L over 2 is a channel 2, and so on, right? And in fact, well, it turns out that if a channel, if a channel is divisible, then it is automatically divisible in an infinite and non-countable number of channels. Yeah, so that's the idea. And the other application is that since the boundary part is already deficient in Gauss rank, which means that if you want to simulate this channel, let's say in a quantum computer, you will need a smaller environment size. So the idea is that one application can be the following. I mean, you can choose EL to be close deficient to, and then, well, basically, this is also a method to find, let's say, Gauss deficient decompositions. And in particular, well, for the qubit, I will show you that this result is particularly interesting, but before, let me explain how that result reduces to a more interesting one for the qubit case. Since for the qubit case, we managed to characterize completely the boundary of the quantum channels from the point of view of divisibility. It turns out that if E is a qubit channel that is not infinitesimal divisible, which means in particular that cannot be implemented even without time-dependent Markovian master equation, then it
So move
is
further.
decomposed in this way, where we have again EL, but the channel in the boundary is indivisible. And the sketch of I mean, the pictorial sketch of the proof is similar to the last one, but the idea is that you have now the set of infinitesimal divisible channels that this CCP. And the idea is that if you take a channel that is outside this set, you always cross the boundary where it has invisible channels. So yeah, so that's the idea. And in particular, it means that any divisible cubic channels, not only full Kraus rank channels, are either indivisible or divisible in an infinite and non-countable number of parts. And okay, let me see. Okay, yes. Regarding the idea that this decomposition can serve as a method to decompose quantum channels, but with the requirement that the channels are Kraus deficient, it turns out that if a cubic channel, a cubic channel is divisible in channels that have at most Kraus rank 2, if and only if it is infinitesimal divisible. Otherwise, at least one factoring channel is Kraus rank no less than 3. Yeah, well, I will pass the sketch of the proof, but well, this fact let us, for instance, to simulate a full Kraus rank channel in a quantum computer, but instead of needing two auxiliary qubits to simulate the environment, because the channel has Kraus rank 4, so then you need an environment of dimension 4. It turns out that if the channel is infinitesimally divisible, you can dispense with a cubic and instead have simply a bit. Yeah, so probably is not such a big application, but the referee asked for this. So. And we implemented this circuit in an IBM Falcon R40 quantum processor. Well, yes, this fidelity, if I remember correctly, is the fidelity between the experimental tree matrix and the theoretical one. So yeah, yes. Yeah, so well, and the idea here is that you can see that, for instance, this part implements the dilation of the boundary part of the channel, and then we prepare again the environmental qubit, and then we implement it to the other part. But the idea here is that you use a smaller quantum register, but you pay this reduction with computational time. Okay, any questions so far? No? Well, since I don't have enough time, probably I will pass this section, or well, the idea of this work, I mean, the general idea was to study measurements where every observable is a particular indexing error. But for instance, if you want to measure this observable with some probability, you would measure the opposite one. So the idea was to define these maps that in turn give us the states that are accessible tomographically when the system has this type of systemic noise. We generalized it to particles using simply the permutation group. We also define a map called that is a coarse grain, in the sense that it also reduces the degrees of freedom aside from the indexing error. And the objectives of this investigation was to characterize these fuzzy maps and quantify how is information lost, and explore different arrangements of particles like this, where, for instance, you have a detector that instead of measuring 9 particles, it can only resolve, let's say, the degrees of freedom of 3 particles, and also the case when where in addition to this, we also have the particle in the indexing error. And well, the part of this work that concerns what happens with the state after measuring with this particular part of noise is still on the investigation with Thomas, Carlos, Gustavo, and others. And for these channels, we characterize the symmetries and so on, and we study how the volume of states is contracted when we have these fuzzy maps, and this result was particularly interesting because, well, if P is the probability to perform the correct measurement, it turns out that the volume of the states or under the action of the fuzzy map shrinks in a doubly exponential ratio with the dimension of the particles, and n is the number of the particles. So the idea here is that even if p is very small, the states that can be accessed with tomography, let's say, is contracted a lot. So if you have, for instance, an experiment or a quantum computer that have this type of error, you are in a big trouble. Okay, and well, we illustrate the action of the fuzzy maps and the coarse graining maps in the scenario where we have entanglement waves. So, for instance, here you have the entanglement that you can see when you don't have noise, when you have noise, and when the detector cannot resolve every particle. So yes, I mean the idea
Zoom
here.
out further.
Oh,
Problemas técnicos con la
ah,
cámara.
yeah.
Alguien que lo pronuncie mejor.
¿Me espera?
Zoom out further.
Well, so the observation here is that even in the case of noise, the interference pattern of the entanglement waves is still a bit preserved, but the decoherence of the channel is present there, right? Okay. Now I am going to talk about Pauli component racing maps. That is, I think, is my most recent work. So, well, the idea here is that, as I told you, the space of quantum channels is big. For instance, if the underlying hyperspace has dimension d, then the set of quantum channels have these quasi-free parameters constrained by these square inequalities that come from the CPTP condition. And for example, only for the cubic case, you have 12 parameters. So the idea is to explore interesting families of quantum channels instead. In particular, if you consider Pauli channels that are just, let's say, rescalings of the components of block vector, where the taus are constrained by these inequalities that come from the CPTP condition. Well, you get a family of quantum channels with with three parameters, and we can even restrict more the family. In particular, we wanted to study the generalization of the maps where these towns are only either 0 or 1. And for the qubit, it defines what we call only component erasing maps, PCE. Some properties is that PCE maps are projectors. They form a subgroup that is finite. So we expect the existence of generators, and not all PCE maps are quantum channels. For instance, the total dephasing channel that shrinks the block sphere into a line from this pole to this pole is a quantum channel because it fulfills the CPTP condition. But for example, if you bring the block sphere into a disk that corresponds to this and is also a PC map, it is not a quantum channel. Well, an interesting observation here is that although you can see that both maps map density matrices into density matrices, well, the CPTP condition forbids this one to be a valid quantum channel. So the idea of this work was to study the generalization of these maps for n qubits. So for n qubits, the density matrices are like this, where these matrices here are called Pauli strings. And yes, so the idea is to solve the problem that comes from the characterization of the complete positivity for this kind of challenge. And one tool that we defined to study, let's say, the patterns and the relations that are formed in these families are these tables. So in the qubit case, this one-dimensional table describes the diagonal of the channel in the Pauli basis. So, for instance, this one is the identity channel because it's 1, 1, 1, 1, 1. Then you have, for instance, the phasing channel because you erase the component Rx and Ry that corresponds to this one. right? And the first component is always 1 because it corresponds to the coefficient that multiplies the identity. So we want to preserve the trace. And for 2 qubits, we indexing this way the diagonal that in this case contains 16 parameters. And for example here we found numerically what PC maps are channels, and we found that some patterns like this one is a channel, but patterns like this is not. And well, the idea was to, well, let's say to figure out the properties and relations that this family has. In particular, for the 2 qubit case, we found numerically and by observation what channels are generators of the semigroup. For instance, we observed that the tables that I show you always have a number of components that is a power of 2 and so on, and a lot of rules like that. But generalizing this for M particles, or even to formalize these observations in a completely analytical way was hard, and in particular it was solved thanks to 2 observations. One is that for the M particle case, where N stands for the number of particles, we found that the eigenvalues of the tree matrix in terms of the house of the channel have this simple form, where A is of this form here, and an identification made by François Lebrun that, well, he observed that for a particular channel 2 taus indexed with these 2 multi indexes are 1, then the tau corresponding to alpha plus beta, where this plus is defined by the line group. The idea here is that if you have a PCE map that fulfills this, and then you compute all possible taus with alpha plus beta, and it turns out that some of them are not 1, then the PCE map is not a channel. But you know how to construct the channel, because You know this. Well, and and other identifications that were used to characterize this family is that the line group is the group part of a finite field that is called the Galois field of order 4. It means that this super tiny field contains only 4 elements. And one super useful observation is that this field has a thing that is called its characteristic. It is equal to 2, and it means that this tiny field is isomorphic to a, to a finite vector space of 4 elements over the prime field with 2 elements. Well, and the so these tricky observations invite us to consider these multi-indices vectors that contain components that can be only 0, 1, 2, or 3 to let's say to identify these vectors with vectors of a finite vector space or over this field. Well, so the idea is that, well, maybe with examples, you will get the idea. Take, for instance, a 2-qubit map that has only the components in black. So one component that is just the index, that is 0, 1, 2, and in the row 0 and alpha 2. So the idea is that you combine these 2 vectors and use the rules from the line group, and then you get the index 1, 1. That is not present here. So then it means that this map is not a quantum channel. But then if you put this component with the properties of the summation, you can prove that alpha 1, alpha 2, and that this vector together, the 0 vector, form a vector subspace, which in that case it means that if that that this map is a quantum channel. That is exactly the case of this one. It has 4 components, and you can prove that under this O plus, it is closed. So it means that it is a vector space, and that this table represents a quantum channel. Well, some properties. Well, I know that is too much now, but I just want to say that, well, the identification of the time group as a part of a field that has a characteristic equal to 2, that basically it means that the most underlying finite field has 2 elements. It translates to the fact that PCE channels have 2 to the K components. Using linear algebra, we also found the generators that are also expected from this semigroup property. And interestingly, the generators can be seen as generalized defacing channels that can be implemented or described with a pure dissipative process with this generator. And since PCE channels commute, then any PCE channel can be implemented with a pure dissipative process with other generators. And just to finish, it turns out also that PCE channels can be implemented in, let's say, in a more physical fashion, basically as an open explicitly as an open quantum system with simple collision models. That it means that if you need n generators to implement it, then it can be seen as a collision of this system with one qubit that is always in the state 0. So in particular for generators, well, you need only one collision. So it's all. Thank you.
Questions?
David, ¿puedes poner la mano para que te siga la cámara? Listo, gracias.
I have 2 questions on definitions. The 2 is, what is Pauli-diagonal and what is grand rank?
Okay. Well, look, Pauli channels are channels that are diagonally Pauli basis, it means that if you have a state, well, I will use this. Yes, if you have a state that is written like this, then the action of the Pauli channel is simply the rescaling of the components of this R. So this vector R describes the completely states for one qubit.
Maybe it's clearer if you write the cross representation.
Yes. Oh, yes.
That is really what you do with your,
What?
that is really what you do with the state. When you see.
Yes. Well, and to answer what is the chaos rank, well, you can always represent channels like this. We put here M equal to 1 Ki rho Ki dagger. So the chaos rank of a channel E is the minimal M that let's say, well, is the number of linearly independent operators that you have here. For example, you can have a channel that can be for instance the summation of 100 unitaries, but if it has chaos rank, for example, equal to 2, you can always find 2 chaos operators such that, let's say, K1 row plus K2 row K2 target.
So is the less number that you have put this in the soup?
Yes.
And the case are ground superior.
Yes.
Thank you.
No question. And I have a question to the last part. These PCE maps,
Yes.
are they independently acting on the qubits? No, right?
What do you mean by dependency? Or
Well, if they are separate, so do one map to the first qubit and another map to the second qubit.
no.
So they
let me try to remember. Well, I actually, well, they generally can live invariant components of the state that concerns many particles. I don't know if it answers your question. I mean,
Again, please.
PCE channels can live invariant components that correspond to observables that act over the whole system.
So they can create entanglement, tangled state.
No, actually, what PC maps can do is only destroy entanglement.
So it's like when they are classically correlated.
To be honest, I don't remember. Probably we never studied that.
David,
Sorry, Thomas.
you say that in that figure that the second one is not a PCE channel.
What?
It's not a PCE channel in the second one.
No, well, both are PC maps.
But
By
in that definition,
definition.
Pauli component is channel or map. It's a PCE map.
Maps. I mean, not every map is a quantum channel. What is easy to define is PCE maps because they are defined, for example, for the qubit as maps that fulfill this and this. But the problem of this work was to characterize what PC maps are quantum channels. That automatically are PC channels because are PCE maps that are quantum channels. So the idea is depicted here that both are PC maps, but this one is not a quantum channel.
But in what sense? Because it's inside the ball block, right?
Yes, but it is not completely positive.
I don't catch why it's not really positive.
Because if you construct E times the identity over some matrix that belongs to the states over your original.
And you just apply it to the Bell state. Don't be so complicated.
What?
Just apply it to the Bell state.
Yes.
You don't need to be so complicated.
Yes. Bell.
Then you don't get the physical, then you don't get the valid state.
Okay, yeah, I understand that expression, but I didn't see why in the figure.
No, you can't see it from the figure.
Yeah, no.
Beyond that. I mean, these are the difference between positive and completely positive.
Yeah.
Channels.
You have to.
You wrote a paper about that.
Yeah, but see, completely positive maps are a finite transformation. That shrink the block sphere and can also translate it, right? And when you translate it, then you can go outside the block Oh. That means that you outside the
Yes, but
set of specific.
it happens also with this one. You can translate the line.
No, that is, okay.
Yeah, I mean the figure is not mine, so that's why yeah. But the idea of that figure is that yes, the line there is from one pole to the another. Yeah, but I mean, you can see complete positivity by looking at that only. Unities.
Yeah.
Okay. Questions?
Any further questions? Okay, then, thanks again.